Ladies and gentlemen, welcome everyone. I am Dr. Roland A. Drolet, PhD in Biomedical Engineering from the University of Toronto, 1971. I am the developer and inventor of the RUMART PEM system that has helped over 1 million people all over the world who were suffering from all kinds of health problems. Today I'm with my son, François Drolet, gold medalist, Olympic gold medalist in Nagano, Japan, in short track speed skating. With this before clip, we have a couple of sheets we want to go through, and I'm going to explain this to you very simply, and you could ask a few questions whenever we stop. So this is about atmospheric gas pollution and how atomic and molecular velocities affect what is in the air. Okay, because in gases, in perfect gas theory that we're going to see in a few minutes, we have little equation that define the macroscopic temperature in Kelvin degrees, which is centigrade degrees plus 273, or 0 Kelvin is minus 273 centigrade. Okay, so actually, the more the temperature is risen, the faster the molecule goes. Just like little, not billiard ball, because billiard balls are much too heavy, but let's say like almost like balloon bubbles, like bubbles, that atoms are like bubbles, and they hit each other elastically. They almost don't lose energy because it comes back with their energy. So this is the basis of assumption of with statistical physics that allow us simply to calculate the average speed of air molecule or molecules in the air, whether it's oxygen, nitrogen, or other molecule like H2O vapor, to calculate the velocity of these atoms and molecules as a function of Kelvin temperature, Boltzmann constant, we'll see its value later on, and the atomic mass or molecular mass. So the heavier is the atom or molecule, the slower it will go. Okay? Because that's the way it is. Okay? So these are probable velocity, average velocity, root mean square for the main square root of velocity. Okay? We are talking of billions of molecules in the air. We'll see in the next page how many molecules there are in 22.5 or 22.4 liters of gas at normal pressure and temperature, which is 20 centigrade degrees. There are 6.02 times 10 to the power 23 atoms or molecule in this quantity of gas, and in let's say 12 grams of carbon, for instance, which is called an atom gram, because the molecular weight of carbon 12 is 12 proton mass. So when we have a mass of carbon like this, that means we have 12 times the mass of the proton. Okay, and so in a, let's say, 12 gram of carbon, of this carbon 12 atom, we call it an atomogram because
Okay.
it's the atomic weight in the quantity of atoms. We call it atomogram. But in one atomogram of carbon or another metal or molecule or a solid, there is exactly the same number as there are atoms or molecules in 22.4 liters. Okay? So
Okay.
this is how we can calculate in a piece of metal how many atoms there are there.
Okay.
And from that, and knowing the dimension of the atom, you can calculate its compactness. So there are all kinds of little things that from macroscopic measurement you can calculate wonderful things, and because atoms are like little balls of proton with electron turning around. But the electrons are going so fast that the different atoms cannot penetrate in each other.
Okay.
So, but they can exchange electrons and they can bind together either, for instance, in covalent bond when they share an electron, okay, but in what we call ionic bond, okay, then these bonds are weaker
Okay.
than, because they are atoms that have, let's say, just one electron on the last shell. So they can live without it, so to speak.
Okay.
And the other one is missing one, but somehow when they have sent one or they gain one, the shell is complete. So it's still a link, but a weak link compared to O2 or H2, okay?
Yeah.
So coming back to what we have here, suppose we have water, the atomic weight of water, H2O. H is one proton, so H2 is 2 atomic weight. O is 16. So atomic weight of H2O is just 18 times the mass of the proton. But when you have, for instance, sodium chloride, table salt or sea salt, then the molecular weight of this is 23 for sodium, 35.45 for chlorine. So that means that this molecule has a molecular weight of 58 proton mass. So it's a heavy mass and it doesn't move fast enough to get in the air
Okay.
like H2O does. And like O2 is staying in the air. O2 is just 32, okay? But what I want you to realize is that this is simple concept from classical mechanics and statistical mechanics. But if we want to understand what happened with in the atmosphere with the pollution, we have to consider the rays coming from the sun, like UV rays that
Okay.
can create ozone, and the chemistry of some of these molecules. For instance, NH3 plus H2O, okay? In water, a certain volume of water can absorb something like 1,000 of its volume of NH3. So there are some affinity between molecules that surpasses what we would think if we didn't consider the chemistry of these bonds.
Okay.
Now I'm going to show you the perfect gas equation I talked about generally, but this is very simple. This is called the perfect gas law, and Avogadro and Boseman constant that I mentioned.
Okay.
They have specific value measured experimentally, but the perfect gas law is what explains what happens in a car motor, for instance. Okay, if you light up the air with gasoline, okay, then you have an impulse of volume sudden impulse of volume. And the temperature doesn't have the time to increase that much, so you have an impulse of pressure. Okay, so that's what transmits the energy in the gas, the chemical energy, into mechanical energy. And energy, remember that energy cannot disappear. It only can be transformed in heat or in something else. Okay, so this simple equation, pressure times volume divided by temperature, is always a constant in perfect gas, depending, of course, on the number of moles, okay, of gas, and the gas time constant. And if you send the temperature in Kelvin on the other side, you see that the product of pressure by the volume is an energy which is dependent on temperature. Okay? So that's why when temperature increases, you get molecules that go faster and faster, like this little equation for the probable, average, and RMS speed. It's because of this equation. When temperature increase, pressure increase, and all these little bubbles, like molecules or atoms, they are always hitting each other in elastic collision, more or less. And we say elastic collision because this theory applies so perfectly to experiment that we know that our theory is right, you know. But of course, when the pressure is not too high, because if the pressure is much too high, then the volume of the atoms, which are not compressible easily as compared to air, the molecules in air, it's almost full of nothing. It's almost empty, okay? But when the atoms are stuck together, like in a metal or liquid, it's very hard to condense more because the molecule, an atom touches, okay? So, so then when the pressure is very high, we really need to take into account the actual volume of all the atoms there, and not only the volume of air, let's say. So here we have the value of the number of atoms or molecules in a mole or in an atom gram. It's 6.02 times to the power 23 atom or molecule, let's say in 22.4 liter of any gas.
Okay.
This is the number of atom molecule, or in one what we call 1 atom gram, for instance, of carbon-12. If it would be carbon-14, which is radioactive, then it would be 14 grams of carbon-14. You have any atoms in this little quantity that you can weigh. So that gives you a sense of going from macroscopic to atomic level. Because the size of the atom is pretty well stable. It doesn't change much with temperature, because temperature is motion of the molecules and atom. It doesn't change the size of the atom. So that's interesting okay. So this is about it. I don't know if you have some question about this, about the Boltzmann constant there. This is the atomic gas constant. R is the macroscopic gas constant, R, but Kb, the Boltzmann gas constant, is the macroscopic gas constant divided by the number of atoms in a mole. So you have 8.31, the gas constant, which is the product of the two, divided by Na, Avogadro number, okay? 10 minus 23 because it's taken up, and you get the value of the atomic Boltzmann constant, which is 1.38 times 10 to the minus 23 joule per atom per degree Kelvin. Okay?
And this is good for perfect gas.
This is good for perfect gas at a temperature for which the pressure is not extremely high. Because when the pressure is very high, for instance, you have to take into account the size of the molecule. And also, if the temperature is decreased to a certain point, then the gas will become solid. I see? So that's where we have, when this happens, when a solid becomes a liquid, this is what we call a phonon frequency, the vibration of these atoms. When it vibrates to a certain temperature, when it gets too fast, the solid breaks and becomes a liquid,
Okay.
and if it goes still faster, it becomes a gas.
Okay.
Okay? So that's what we call a phase shift in engineering or chemical engineering. Okay, is that
Yeah.
understandable?
Yeah.
Okay, very good. Thank you very much.
Thank
That's a little clip to show that we may not be perfect gases, but we know that when we have too much pressure in our gastric places, we get this equation working, and it makes what you know. Okay, so take care, have a good day, and smile. So that's the end of this clip. Thank you for your attention. I hope you enjoyed it. And please keep smiling till the next clip.